There is an equation that decides whether you live or die before you ever leave the ground. It was written in 1903 by a deaf Russian schoolteacher who never built a rocket in his life. He worked it out on paper in a small house, surrounded by tin models and the silence of a man who could not hear the world around him. And the strange, uncomfortable truth is this: that equation has never once been beaten, not by NASA, not by the Soviets, not by the most expensive engineering programs in human history, not by anyone. It cannot be argued with, negotiated with, or outfunded. It does not care how badly you want to go to Mars, and it does not care how many billionaires promise you a ticket. It is just math, cold, exponential, and final. And when you actually run the numbers through it for a return trip from the surface of Mars, something quietly horrifying happens. The math stops giving you a spaceship and starts giving you a coffin. This is the part of the Mars conversation that almost nobody wants to talk about. We talk about the launch, we talk about the landing, we talk about flags and footprints and the first photographs of human boots in red dust. We talk endlessly about getting there. What we don't talk about, not honestly, is the line in the equation that has to balance for anyone to ever come back. Because reaching Mars is, in the brutal language of physics, the easy half, the cheap half, the half we've basically already solved. It's the second half, the return, where the equation turns on you. And it turns on you in a way that a different physicist, one you've definitely heard of, spent the last years of his life warning us about. His name was Richard Feynman, and before we put a single number on the screen, you need to understand why he matters to a video about Mars, because he is the reason this whole thing has a name. In 1986, the Space Shuttle Challenger broke apart 73 seconds after launch, killing everyone on board. Feynman, already sick with the cancer that would eventually take his life, was pulled onto the commission that investigated why. And what he found wasn't really about a rubber seal, even though that's the part everyone remembers. What he found was an organization that had started believing its own press releases. Managers who had quietly convinced themselves the risk was 1,000 times smaller than the engineers screaming from below were telling them. People who had begun to treat a hope as if it were a fact. Feynman ended his report with one sentence. He wrote that for a successful technology, reality must take precedence over public relations because nature cannot be fooled. Nature cannot be fooled. Sit with that for a second, because that single idea is the entire spine of this video. You can fool an investor, you can fool a crowd, you can fool yourself. You cannot fool the rocket equation. And the rocket equation is the thing standing between a human being on Mars and that same human being ever seeing Earth again. And there's a moment from that investigation worth telling because it captures in one image exactly the kind of honesty this whole subject demands. The official hearings were full of complicated testimony, charts, probabilities, careful corporate language, everyone talking around the problem. The seals on the shuttle's boosters were suspected, but the question of whether the cold weather on the morning of the launch had made them fail was buried under layers of qualification and doubt. So Feynman did something almost rude in its simplicity. In the middle of a televised hearing, he took a sample of the rubber sealing material, squeezed it in a small clamp, and dropped it into his glass of ice water, the same ice water that had been sitting in front of him. After a few minutes, he pulled it out, released the clamp, and showed everyone that the cold rubber didn't spring back. It stayed squashed. It had lost its resilience in the cold, exactly as it would have on that freezing launch morning. No equations on a slide, no corporate hedging, just a piece of rubber, a glass of cold water, and a truth that no amount of testimony could talk its way around. The material either bounces back in the cold or it doesn't. Nature cannot be fooled. That is the spirit I want to carry through this entire video, because the Mars return is full of the same kind of comfortable, complicated talk that surrounded those seals, and what we're going to do is the equivalent of dropping the rubber in the ice water. We're going to take the plan, the beautiful, live-streamed, flag and footprint plan, and we're going to squeeze it in the clamp of one equation and see whether it springs back. Spoiler, written into the title, it doesn't, not yet. So that's the deal we're making for the next couple of hours. No hype, no mythology, no tragedy dressed up as progress. just the one equation almost nobody puts on screen, what it actually says and why, when you point it at the surface of Mars and ask it the only question that matters, can these people come home, it keeps returning the same answer. Not yet, maybe not ever, not like this. Konstantin Tsiolkovsky lost most of his hearing at the age of 10 to scarlet fever. In the Russia of the 1870s, a deaf child was essentially written off. He couldn't attend a normal school, so he taught himself, in libraries, out of borrowed books, with a kind of obsessive patience that only isolation can produce. And while everyone else around him was dreaming about flying machines in the vaguest, most romantic terms, Tsiolkovsky did something almost nobody else was doing. He asked the boring question, the engineer's question, the Feynman question, decades before Feynman. Not wouldn't it be wonderful to fly to the stars, but how much would it actually cost in fuel to do it? And in 1903, the same year the Wright brothers got a powered aircraft off the ground for 12 seconds, this half-deaf school teacher published a formula that described, with perfect accuracy, the fundamental problem of all space travel that would ever happen forever. He had no rocket, he had no engine, he had no test stand and no budget and no government behind him. He had a pencil and he had honesty, and it turned out that was enough to see 100 years into the future. What he understood was deceptively simple to say and devastating to live with. A rocket moves by throwing mass out the back. You burn fuel, you shoot it out of the nozzle at high speed, and the rocket gets pushed the other way. That's it. That's the whole principle. Every rocket that has ever flown, from the first crude military missiles to the machine that carried men to the moon, works on exactly that idea. You push against the stuff you're throwing away. It's worth pausing on how alone Tsiolkovsky was when he saw this, because it tells you something about the nature of the truth he found. He wasn't part of a great laboratory. He had no colleagues to check his work, no funding body to impress, no rival to race. He was a provincial schoolteacher, nearly deaf, scribbling in a country that thought of him, when it thought of him at all, as an eccentric. He built little models out of tin and paper to test his ideas about flight. He imagined, decades before anyone could attempt them, multi-stage rockets and orbiting stations and the use of liquid fuels, the very things that would eventually make spaceflight real. And the reason his equation has lasted, the reason it still rules every mission today, is precisely that it didn't come from ambition or salesmanship. It came from a man with nothing to sell, asking only what was true. That's why it can't be fooled. It was never trying to flatter anyone in the first place. But here is the trap. Here is the thing that turns a simple idea into a curse. The fuel you need for the end of the journey you have to carry from the very beginning, which means the fuel itself has weight, which means you need more fuel just to carry the fuel, which means that fuel also has weight, so you need even more fuel to carry the fuel that carries the fuel. And on and on and on. It feeds on itself, it compounds. And anything that compounds doesn't grow in a nice, gentle, straight line. It grows exponentially. It explodes upward in a curve that starts off looking manageable and then very suddenly becomes a wall you cannot climb. That is the secret at the heart of the rocket equation. The relationship between how much speed you want to gain and how much fuel you need to gain, it is not a straight line. It is an exponential. And exponentials are the single most counterintuitive thing the human brain has to deal with because our instincts are built for straight lines. We think that if a little more speed costs a little more fuel, then a lot more speed costs a lot more fuel. That feels obviously true. It is completely, catastrophically wrong. Engineers have a grim little nickname for what Tsiolkovsky discovered. They call it the tyranny of the rocket equation. Tyranny. Not the challenge of the rocket equation, not the difficulty of it. The tyranny. Because a tyrant is something you cannot reason with, something that imposes its will regardless of how you feel about it. And that's exactly what this equation does. It sits over every space mission ever planned like an unmovable judge, and before you build anything, before you spend $1, it tells you whether your dream is allowed to exist. So let's actually understand the tyranny in plain language before we ever point it at Mars. Because once you feel it in your gut, the Mars problem stops being a mystery and starts being something far worse. It starts being obvious. Forget the symbols for a moment. I'm going to give you the equation as a feeling first, then we'll put the numbers on it. Imagine you want your rocket to gain a certain amount of speed. Physicists measure this in a quantity called delta V, which just means change in velocity, change in speed. Every maneuver a rocket performs, climbing off a planet, steering between worlds, slowing down to land, costs a specific, non-negotiable amount of delta V. You can think of delta V like the total range on a tank of gas, except instead of measuring distance, it measures how much you can change your motion. It is the true currency of space travel. Not money, not time, delta V. Everything you want to do in space has a price tag written in delta V, and you must pay it in full, in fuel, up front. Now here's the cruel part. The amount of fuel you need doesn't add up as the delta V goes up. It multiplies. There's a number that engineers call the mass ratio, and it's just the weight of your fully fueled rocket divided by the weight of your empty rocket. The bigger the speed change you want, the bigger this ratio has to be, and it climbs that exponential curve we talked about. Let me make this concrete, because this is the moment the whole thing clicks. To climb off the surface of the Earth and reach orbit, a rocket needs roughly 9.5 kilometers per second of delta V. That's the price tag for the single hardest thing humans routinely do in rocketry. And when you feed that number into Tsiolkovsky's equation using ordinary chemical fuel, the kind that actually exists and works, you get a mass ratio of around 20. 20. That means for every single kilogram of rocket you want in orbit, the metal, the engines, the crew, the payload, the spacecraft itself, you need around 20 kilograms sitting on the launch pad. 19 of those kilograms are fuel that gets burned and thrown away. One of them is the thing you actually cared about. Turn that around and look at it from the other direction, because it's even more brutal that way. It means a rocket leaving Earth has to be something like 90 to 95% fuel by weight. 95%. The rocket is essentially a colossal flying tank of explosive liquid with a tiny, almost insulting little capsule perched on the very top. Everything you've ever seen launch, the towering machines, the fire, the smoke, the thunder, almost all of that is fuel. The actual spacecraft is the cherry on a mountain of gasoline. And here's where the exponential reveals its teeth. What happens if you want just a little more delta V? What if the mission needs 10.5 kilometers per second instead of 9.5? You'd think, fine, a bit more fuel, maybe 10% more. No, because of the exponential, that small bump in speed doesn't cost you 10% more fuel. It can cost you 30, 40, 50% more, because every extra unit of speed gets multiplied through that compounding curse of carrying fuel to carry fuel. There's a reason engineers fight to the death over a few hundred meters per second in a mission plan. There's a reason they'll redesign an entire spacecraft to shave off 100 kilograms. They're not being fussy. They're running from the exponential. They know that the equation punishes ambition in a way that feels wildly unfair because it is not linear, and our intuition is, this is the tyranny. A small increase in what you ask for produces a violent, sometimes mission-killing increase in what you must pay, and the equation never blinks. It never gives you a discount. It never rounds in your favor. Let me make you feel the exponential in your bones, because everything that follows depends on you truly believing it, not just nodding along. Picture a staircase, except this is no ordinary staircase. The first step is normal height. The second step is a little taller. The third is taller still, and each step keeps growing, faster and faster, until somewhere up ahead the steps are taller than buildings, taller than mountains, and no leg in the universe could ever climb them. That's an exponential. It looks gentle and walkable right at the start, which is exactly why it fools you, and then it turns into a cliff. Now, here's the thing that should keep you up at night. Delta V is the staircase. Every kilometer per second of speed you want is another step. And down at the bottom, where we get off Earth and coast to Mars, the steps are tall but climbable. We've built machines that can take them. But the return from Mars asks you to climb the staircase again from a place where you have to build your own legs out of the dirt before you can even start. Here's another way to see it that I find clarifying. Suppose, magically, your rocket fuel were free of weight. Weightless fuel. In that fantasy world, the rocket equation barely exists, and going anywhere is easy, because you could just strap on as much fuel as you wanted at no cost and accelerate forever. The entire reason space is hard, The entire reason Tsiolkovsky's equation is a tyrant instead of a footnote is that fuel has mass, and mass has to be carried, and carrying it costs fuel. Every problem in this video, every single one, traces back to that one sentence. Fuel weighs something, so you have to spend fuel to move your fuel. Hold that sentence. It is the seed from which the entire nightmare of the Mars return grows. And there's a detail in the work numbers that I skipped past, but you should see it head on, because it's where the cruelty really lives. When we said leaving Earth needs a mass ratio of around 20, that came from running about 9.5 kilometers per second through the equation with realistic chemical fuel. Now watch what happens to that ratio as the delta V creeps up. At 9.5, you need roughly 20 kilograms on the pad per kilogram delivered. Nudge the requirement up by just 1.5 kilometers per second, and that 20 doesn't become 23 or 25. It can leap toward 30 or beyond. The cost per extra step isn't constant, it accelerates. The higher you've already climbed, the more savagely each additional step punishes you, because you're now paying the exponential on top of the exponential you already paid. This is why a mission that's almost affordable can become flatly impossible from a change that sounds, to a normal human ear, completely trivial. A little more speed, a little more payload, a little more margin for safety. The equation hears a little more and answers with a wall. This is the tyranny. And it's why, when an engineer tells you a mission is marginal, they don't mean it's a coin flip. They mean it's sitting on the steep part of the staircase, where the smallest thing going wrong, a heavier than expected vehicle, a slightly lower performing engine, an extra maneuver nobody budgeted for, doesn't cost you a little. It costs you everything. It pushes the mass ratio past what any real material can be built to survive, and the dream quietly stops being allowed to exist. Now, humans are clever. We didn't just accept this and give up. We found the one and only real loophole, and it's worth understanding because it's the trick that lets us reach orbit at all. The loophole is called staging. If almost all your rocket is fuel inside heavy metal tanks, then as soon as a tank is empty, that metal becomes dead weight you're dragging along for no reason, so we throw it away. Mid-flight, we build the rocket in sections, and as each section burns dry, we drop it so the remaining engines don't have to haul empty tanks. That's why a rocket to orbit comes apart in pieces as it climbs. Every piece it sheds is the equation being cheated, just a little, by refusing to carry dead weight any further than necessary. Staging is the reason we can get to space at all. Without it, a single-stage rocket trying to reach orbit on chemical fuel would need to be something like 96% fuel, leaving barely 4% for the engines, the structure, the heat shielding, the landing gear, and the payload combined. And aluminum and steel and human beings simply cannot be built that light. People tried. In the 1990s, there were serious, well-funded programs to build a single-stage-to-orbit vehicle, machines with names like the Delta Clipper and the Venture Star. They all ran straight into the same wall, the mass budget, the equation. They got cancelled, every one of them, because nature could not be fooled. The fuel fraction they needed didn't leave enough room to build a real machine. The dream was beautiful. The math said no. I want you to really feel what staging is, emotionally, because it's a kind of controlled desperation, and it tells you how close to the edge we live even on our home planet. A rocket climbing off Earth is in a sense eating itself alive to escape. It builds tanks, fills them with fuel, burns that fuel, and then the instant a tank is empty, it tears that tank off its own body and lets it fall away, because to carry the empty weight even a moment longer would be to lose the race against the exponential. A rocket to orbit is not really one machine. It is a sequence of machines, each one sacrificing itself so the next can continue, each one dropping away the moment its usefulness ends, until only a small final stage and its precious payload coast on into orbit. It looks majestic from the ground. Up close, in the logic of the equation, it's frantic. It's a creature shedding pieces of itself as fast as it can, because the math gives it no other way to win. That is what it takes on Earth, with everything in our favour, just to reach orbit. That is the ferocity of the tyrant we're up against. And now hold that image against Mars one more time, because it sharpens the whole problem. On Earth, we can be that frantic, self-devouring creature, because we have a civilization that builds these multi-stage machines by the dozen, stacks them, fuels them, and forgives the staggering waste of throwing most of each one away. On Mars, you cannot afford to be that creature. You have one machine, and you cannot shed pieces of it across a planet you've barely begun to understand, because you cannot build the replacement. The single greatest weapon we have against the rocket equation, the willingness and the industrial capacity to throw our rockets away in pieces, is a weapon we mostly have to leave at home when we go to Mars. We arrive at the second staircase having surrendered the very tool that got us up the first. So hold on to that. Even getting off the Earth, the planet we evolved on, the planet with all our factories and all our engineers and all our money, requires the single most extreme engineering trick we have, just to barely squeak past Tsiolkovsky's curse. We win, but we win by the thinnest possible margin, and only by throwing most of our rocket away on the way up. Now, keep that picture in your head. The 95% fuel, the throwing away of tanks, the fight over every 100 meters per second. Keep all of it, because now we're going to Mars, and on Mars, you don't get to throw anything away. On Mars, there is no factory. On Mars, there is no second rocket waiting. On Mars, you have to do the hardest thing in rocketry, the climb to orbit all over again, except this time, you have to do it after carrying everything you need across 140 million miles of empty space first. And the equation is waiting for you when you arrive. I know how strange it sounds to call a 7-month voyage through deep space the easy half. Nothing about it feels easy. But in the language of the equation, in the language of delta V, getting to Mars is genuinely the part we've mostly figured out. And understanding why is the key that unlocks the whole nightmare of the return. Here's the thing that breaks most people's intuition about space. The hardest part of going anywhere is not the long, lonely cruise between worlds. The hardest part is the very beginning, fighting up out of a planet's gravity. Once you're in space, once you've paid that enormous toll to escape Earth's pull, moving between planets is comparatively cheap. Space is empty. There's no air to push against, no friction to fight. You give yourself a shove in the right direction at the right moment, and then you coast. For months, yes. Across unimaginable distances, yes. But you coast for free, because nothing is slowing you down. The galaxy does the work. You just have to aim. Let me put delta V numbers on the trip, the same currency we've been using. Climbing off Earth to low orbit, as we said, costs around 9.5 kilometers per second. That's the giant. Then, from orbit, the push that flings you onto a path toward Mars, the maneuver engineers call transmars injection, costs only another 3.5 to 4 kilometers per second or so. Notice how much smaller that is. You spent 9.5 just to get off the ground, and then a fraction of that throws you literally to another planet. That's the empty space discount. That's why the cruise is the cheap half. And arriving at Mars is, if anything, an even bigger gift, because Mars hands you something almost for free, something it took us decades to learn how to exploit. Mars has an atmosphere. It's a thin, wispy, almost useless atmosphere for breathing, less than 1% the thickness of ours. But it is thick enough to do one priceless job. It can slow you down. Instead of firing your engines to break into orbit, burning precious fuel to lose speed, you can plunge into the top of that thin Martian air and let friction do the braking for you. We call it aerobraking or aerocapture, and it means that most of the cost of stopping at Mars gets paid not in fuel, but in heat shielding, in physics, in the planet's own atmosphere doing the work. The descent down to the Martian surface, the part that feels so terrifying, the screaming entry and the parachutes and the rockets, costs less than a single kilometer per second of delta V in fuel terms, because the air gave you the rest as a gift. And the path itself, the route across the solar system, is chosen by the same logic of cheapness. The standard way to get to Mars is along what's called a Hohmann transfer, named after a German engineer who, like Tsiolkovsky, worked it out on paper long before anyone could fly it. The idea is elegant. Instead of pointing at Mars and burning fuel the whole way, which would be insanely expensive, you give yourself one well-timed push that drops you into a long, lazy elliptical loop around the Sun, an orbit whose far edge just kisses the orbit of Mars at exactly the moment Mars arrives there. You spend almost the entire journey coasting along that ellipse with the engines off, falling around the sun, letting gravity carry you. It's not the fastest route, it takes the better part of 7 or 8 months, but it is very nearly the cheapest, and cheapness, in the currency of delta V, is what makes a mission possible at all. The minimum energy version of this Earth to Mars loop costs only a handful of kilometers per second once you're already in space, a bargain compared to the giant toll of leaving Earth's surface. But that elegant coasting path only exists at specific moments, and this is where we get our first taste of a tyrant we'll meet again later in a far crueler form. Because both planets are moving, the gentle ellipse that connects them only lines up correctly about once every 26 months. Engineers map these opportunities on a chart with a strange name, a pork-chop plot, so called because the curves of equal fuel cost, plotted against departure and arrival dates, trace out lobes that look a little like a pork chop. The plot shows you, at a glance, the narrow windows when the trip is affordable, and the vast stretches of time when it simply isn't, when the planets are so badly positioned that no reasonable amount of fuel could bridge the gap. For now, on the way out, this is just a scheduling detail, a launch window you wait for. Remember that it exists and that it cuts both ways. It will come back to decide whether anyone gets to leave Mars at all, so add it all up from the equation's point of view. The expensive thing, leaving Earth, we've solved with staging. The cheap thing, crossing space, the galaxy does for us. The arrival, the atmosphere of Mars hands us a discount. Every single step of the journey there either has a known solution or comes with a built-in break. The math, while enormous, balances. We can do it. We have in fact sent dozens of robotic spacecraft to Mars exactly this way. The path there is a paved road. Let me put one comparison on the table that I think crystallizes the whole asymmetry of this video. If you tally up the delta V for the entire round trip, surface of Earth to surface of Mars and all the way back to the surface of Earth, the total is genuinely staggering, well over a dozen kilometers per second when you account for every climb and every break. But look at how that total is distributed, because the distribution is the entire story. The single biggest chunk, by far, is leaving Earth, and we've mastered that. The crossings, there and back, are comparatively cheap, paid in coasting. The arrival at Mars is discounted by its atmosphere. And then there's that one stubborn, unavoidable, roughly 4.25 kilometers per second climb off the surface of Mars, which sounds modest next to Earth's 9.5, but which has to be paid with fuel you don't have, from a launch site that doesn't exist, by a machine that's been rotting in the cold for a year, flown by a crew the weight has weakened, with no second try. The numbers on the way out are bigger and easy. The number on the way back is smaller and nearly impossible. That inversion, big and easy versus small and impossible, is the secret the equation has been keeping, and it's why the return, not the journey, is where Mars missions go to die. This is why every flashy Mars presentation spends 90% of its time on the journey there. The rocket on the pad, the fire, the trajectory animation curving gracefully across the solar system, the capsule streaking through the Martian sky under a parachute. It's all real, it's all hard-won, and it's all the part where the equation is on our side. It makes for an incredible show. And it is, in the most important sense, the half of the problem that was never really the problem. Because now your astronauts are standing on the surface of Mars, they've planted the flag, they've taken the photo, the hard journey is behind them, or so the story goes. And then someone has to answer the question that the whole spectacle was carefully built to make you forget. How do they get back up? Here is the sentence that the entire Mars colonization industry is built on quietly not finishing. To come home from Mars, you have to do the single hardest thing in all of rocketry, climbing off a planet and into orbit a second time. Except now you have to do it from a place with no launch tower, no ground crew, no factory, no fuel depot, and no second chance. Stop and really absorb the shape of that, because it's the hinge the whole video turns on. On Earth, the climb to orbit is the hardest thing we do, and we throw the entire might of a civilization at it. Decades of engineering, factories the size of towns, launch towers taller than skyscrapers, armies of specialists, mountains of fuel refined in industrial plants and pumped into the rocket as it sits safely on the ground. And even with all of that, we barely win, by the thin margin that staging buys us. That is the difficulty of climbing off a planet, fully supported, at home. Now take all of that support away. Take away the factory, the tower, the ground crew, the refinery, the spare rocket, the ability to try again next week. Move the whole thing 140 million miles from the nearest help, and then demand that the climb happen anyway, perfectly, once. That is the Mars return. It is the hardest thing we know how to do, attempted under the worst conditions we can imagine, with every advantage stripped away. People hear Mars has weaker gravity and assume the climb off Mars must therefore be easy, a gentle hop compared to Earth's violent ascent. We're about to see exactly why that intuition is a trap, and why the equation once again refuses to give the discount our instincts expect. Let's get the number, because the number is everything. To climb from the surface of Mars up to a low Martian orbit costs roughly 4.25 kilometers per second of delta V, once you account for the losses you take fighting gravity on the way up. Now your first instinct, having heard that Earth's climb costs 9.5, is probably relief. 4.25? That's less than half of Earth's toll. Mars is smaller, its gravity is weaker, only about 38% of ours. Surely this is the easy version of the climb. And that instinct is exactly the trap the equation sets for you. Because remember the tyranny. Remember that fuel needs don't add, they multiply, and they climb an exponential curve. 4.25 kilometers per second is not a bit less than half the difficulty of leaving Earth. When you run it through Tsiolkovsky's equation, it still demands a mass ratio of around 3:4 for a decent engine, which means your Mars ascent vehicle, the machine that lifts your crew off the surface, still has to be somewhere around 70 to 80% fuel by weight. 70 to 80%. Just like on Earth, the spacecraft is mostly a tank of propellant with a small crew capsule on top. The exponential doesn't let Mars off the hook just because it's smaller. It just makes the number a little less suicidal than Earth's, while still being enormous. So now the real question crystallizes, and it is the question this entire video exists to answer. Where does that fuel come from? On Earth, the answer is trivial. We have refineries, we have pipelines, we have an entire planetary civilization built around manufacturing rocket propellant, and we have a launch tower to fuel the rocket up while it sits comfortably on the ground. On Mars, you have none of that. You have rust-colored desert, a toxic atmosphere, and whatever you manage to drag across 140 million miles of space with you. And here's where the exponential turns from a curse into a closing trap, because now it eats itself. Watch carefully, because this is the heart of the whole thing. Option 1. You bring the return fuel with you from Earth. Fine, but that return fuel has weight, a lot of weight, because remember, the ascent vehicle is 70 to 80% propellant. So now your spacecraft leaving Earth has to carry not just the crew, not just the supplies, not just the lander, but also the entire mass of fuel needed to launch off Mars later. And that fuel has to be hauled all the way to Mars and landed gently on the surface. But to land extra weight on Mars, you need a bigger lander. And to fly a bigger, heavier spacecraft to Mars in the first place, you need more fuel leaving Earth. And to lift that extra Earth departure fuel off the ground, you need an even bigger rocket, which needs even more fuel. The exponential which we beat by staging on the way up from Earth comes roaring back, because every kilogram of return fuel you carry forces you to carry many more kilograms of other fuel just to move it. You are now paying the rocket equation's tax not once, but stacked on top of itself over and over. The numbers don't just get big, they run away from you. They spiral up that exponential wall until the rocket you'd need to leave Earth becomes absurd, a machine too large to build, hauling tanks across the solar system just to use them once, at the very end, after sitting full of explosive cryogenic liquid for over a year in deep space and on a freezing alien surface. This is not a small inconvenience. This is the reason the simple, honest plan, just bring the fuel with you, has been quietly abandoned by essentially every serious mission architecture. The equation forbids it, not difficult, forbidden. The mass spirals past anything we can launch. And I want to put a finer point on just how vicious this self-eating spiral is, because the numbers, when you actually trace them, are almost comic in their hopelessness. The return propellant for a crewed ascent vehicle is measured not in kilograms, but in many hundreds of tons. Methane and oxygen together, enough to lift a heavy crewed vehicle off Mars, runs to something well over 1,000 tons of propellant in the larger architectures. Now imagine you decided to bring all of that from Earth, fully fueled, ready to use. First, you have to land all of it on Mars gently, which we've already established we don't know how to do for heavy masses. But set even that aside, to send 1,000+ tons of return fuel to Mars, you first have to push that 1,000 tons onto a trajectory toward Mars, which costs its own delta V, which means its own fuel. And to lift that 1,000 tons of return fuel, plus the fuel needed to send it, off the Earth in the first place, you're back at the bottom of the 9.5-kilometer staircase, with the heaviest payload imaginable, paying the worst version of the exponential there is. The rocket you'd need becomes a structure that dwarfs anything ever built, most of it fuel to move fuel to move fuel, and at the end of that monstrous chain, the fraction that's actually useful crew and cargo is vanishingly small. The equation doesn't just say this is expensive, it says the machine collapses under its own logic before it ever flies. There's a second, quieter killer hiding inside the bring it with you plan, and it's one almost nobody mentions. Even if you could somehow launch and land all that fuel, you'd have to keep it. Rocket propellants like methane and oxygen are only useful as liquids, and to stay liquid they have to be kept brutally cold, hundreds of degrees below zero. In the warmth of space sunlight, and across the better part of a year of travel, plus over a year sitting on the Martian surface, those propellants slowly boil away. Engineers call it boil off, and fighting it requires constant power and refrigeration, more systems that have to work flawlessly for years, more mass, more things to fail. So the fuel you so painfully hauled across the solar system would be quietly evaporating the entire time, and you'd arrive at the moment of truth, the launch window, with less than you started? Possibly not enough. The equations set the price. Physics then charges you interest on it in the form of fuel that refuses to sit still and wait. So between the runaway exponential and the boil-off, the honest verdict on bringing your return fuel from Earth is not hard, it's no. And that single no is what forces the entire mission down a far more dangerous road, the road where you try to make the fuel on Mars instead. Which sounds, when you first hear it, almost reasonable. It is not. So the planners turn to option 2, and option 2 is where hope quietly replaces math. If you can't afford to bring the return fuel, then you have to make it. On Mars, from scratch, out of the planet itself. This idea even has a reassuring, technical-sounding name. In-situ resource utilization. In-situ just means on-site, in place. The pitch is elegant, almost beautiful in its logic. Mars's atmosphere is about 95% carbon dioxide. Carbon and oxygen just sitting there in the air, the raw ingredients of rocket fuel. So you bring a chemical plant, you suck in the Martian air, you add some hydrogen, and through a chemical reaction discovered in the 1800s, you brew your own methane and oxygen right there on the surface. Then you fill your ascent vehicle with the fuel you made from the planet, and you fly home. The planet pays for your ticket back. It's clever. It really is clever. And I want to be fair to it, because the cleverness is real and the appeal is genuine. This is the single idea that lets the Mars return escape the impossible spiral we just watched, consume the bring it with you plan. If, and it's the largest if in all of spaceflight, you can make the fuel on Mars, then you don't have to launch it from Earth, which means you don't have to land it on Mars, which means you don't have to balloon your Earth rocket into a monster, which means the whole runaway exponential quietly relaxes. On a presentation slide, it looks like the master key. One clever process, and the locked door swings open. This is why it appears in essentially every serious plan to bring humans home from Mars. There is no other answer that even pretends to work. The fuel either gets made on Mars, or there is no return at all. That is the weight this single idea is carrying, and it is also right now, today, the single most undertested, hand-waved, load-bearing assumption in the entire dream of human Mars exploration. Let me walk you through what it actually requires, not as a cartoon, but as the chain of physical miracles it really is. Because every link in this chain has to hold perfectly for years with no one to fix it, or your astronauts simply never leave the ground. First, the reaction itself. The favoured method is called the Sabatier reaction. You take carbon dioxide from the Martian air and combine it with hydrogen, and with the right catalyst and the right heat, you get methane and water. The methane is your fuel. You then split the water with electricity into hydrogen and oxygen. The oxygen is your oxidizer, the thing the fuel burns with. The reclaimed hydrogen gets fed back into the process. On paper, it's a tidy loop. In a laboratory on Earth, it works. We've done it in clean rooms with technicians standing by and a wall socket for unlimited power. But notice what the reaction needs. It needs hydrogen, and here is the first crack in the elegant plan. Mars's atmosphere has almost no hydrogen in it, so where does the hydrogen come from? Two options, and both are brutal. Either you carry it from Earth, in which case you're back to hauling mass across space, defeating part of the point, and hydrogen is the single most annoying substance to store in all of engineering, a tiny molecule that leaks through solid metal and has to be kept colder than almost anything in the universe. Or you get your hydrogen from Martian water, which means you have to find water, extract it, and that opens up an entirely new chain of miracles. Because the water on Mars is not in a reservoir with a tap. It's locked underground as ice, mixed into the frozen soil, buried beneath meters of rock and regolith in many places. To get it, you have to drill, on another planet, with a robotic system that has to work autonomously, in temperatures that swing over 100 degrees in a single day, through soil laced with perchlorates, toxic chlorine salts that corrode equipment and poison people. You have to drill, extract, heat, and purify the water, all before the chemistry can even begin, and we have never drilled for water on Mars. Not once. The deepest any spacecraft has ever dug into Mars is measured in centimeters, scratching the surface, sometimes failing to even do that. The plan requires industrial-scale subsurface mining on a world where we have so far managed to gently poke the dirt. Now stack the power requirement on top. All of this, the drilling, the heating, the chemical reactor, the splitting of water with electricity, the compression and freezing of the fuel to keep it liquid, all of it is enormously energy hungry. We are talking about needing a power plant on Mars, running continuously, reliably for over a year through dust storms that can blot out the sun for months, in cold that freezes lubricants solid and makes metal brittle. Solar panels alone won't reliably do it, because the same dust that we'll talk about later coats them, and the storms can drop their output to a tiny fraction of normal. So most serious plans now require a nuclear reactor landed on Mars, set up and operated by a tiny crew or by robots, with no maintenance crew and no replacement parts. And here's the timing detail that I find genuinely chilling, the one that turns this from an engineering challenge into something darker. The plan, in most architectures, is that you don't even send your astronauts until the fuel is already made. You land the chemical plant and the empty ascent vehicle years ahead of the crew, robotically, and you let it manufacture and store the entire return propellant load before a single human being departs Earth. Why? Because no one is brave enough or foolish enough to send people to Mars and only then start trying to make the fuel that brings them home. The risk is too obvious, so the rule becomes, the fuel for the trip home must already exist, sitting in tanks on the Martian surface, confirmed and verified, before the humans are allowed to leave Earth at all. Think about what that quietly admits. It admits that the people planning this know, deep down, that the fuel manufacturing is the part most likely to fail. It admits that they don't trust it enough to do it with lives already committed on the surface. The entire architecture is shaped around the fear that the fuel won't be there. And they're right to be afraid, because we have never, not one single time, manufactured rocket fuel on the surface of another world. We have never operated a chemical plant on another planet. We have never run a nuclear reactor on Mars. We have never drilled for and extracted Martian water. Every single one of these is a first, and the plan requires all of them to work, in sequence perfectly, autonomously for years, with the lives of the crew riding on the assumption that they did. Let me make the autonomy part vivid, because this is where people's intuition fails them most. When a chemical plant on Earth has a problem, a valve sticks, a pump cavitates, a sensor drifts, a filter clogs, a pressure climbs where it shouldn't, a human walks over and fixes it, often within minutes. Chemical plants on Earth are crawling with technicians precisely because complex chemistry at industrial scale is finicky and wants to go wrong. Now move that plant to Mars, take away every technician, and put the nearest human help somewhere between 3 and 22 light minutes away. The plant has to detect its own faults, diagnose them and correct them entirely on its own, or limp along until a fix can be radioed from Earth across a delay long enough that the situation will have changed before the instruction arrives. It has to do this not for a week, not for a month, but continuously for the better part of a year or more, through dust storms, through temperature swings of over 100 degrees in a single Martian day, through the slow grinding infiltration of that electrically charged dust into every moving part. We do not have chemical plants on Earth that run for a year untouched by human hands. We're proposing to build one that does it on Mars on the first try, with lives depending on the output. And consider the catalysts and membranes at the heart of the Sabatier process, the special materials that make the chemistry happen at all. They have to keep working despite constant radiation exposure, despite thermal cycling that expands and contracts everything every single day, despite contamination from the very dust we keep returning to. Catalysts degrade, membranes foul and tear. On Earth you replace them on a schedule. On Mars there is no replacement, no schedule, no resupply, only whatever spares you manage to land and whatever a crew with limited tools and limited expertise can manage to swap out. Every consumable that wears out is a countdown timer you cannot reset. Then there's the water itself, and I want to linger on the drilling, because the phrase extract water from Mars hides an enormous amount of difficulty. The accessible water ice isn't sitting in a convenient lake. In many promising locations it's mixed into the frozen ground, beneath the layer of dry regolith and rock, and getting it means drilling down through material that is hard as rock and cold enough to be brittle, contaminated with toxic perchlorate salts that corrode your equipment and would poison the crew. A drill on Mars has to deal with the dust working into its mechanism, with the extreme cold seizing its moving parts, with the lack of anyone to clear a jam or replace a worn bit. And it has to do this reliably enough and at a high enough rate to feed a chemical plant that needs to produce hundreds of tons of propellant before a launch window opens. The most we have ever dug into Mars is a scratch, centimeters deep, and even those attempts have sometimes failed when the soil behaved differently than expected. The plan needs industrial subsurface mining. We have managed so far to occasionally and unreliably poke the dirt. And don't forget the power plant sitting behind all of this, because every step, the drilling, the heating, the chemistry, the splitting of water, the compressing and freezing of the fuel to keep it liquid, is ferociously hungry for energy. We're talking about needing a genuine power station on Mars, running without interruption for over a year. Solar can't be trusted for it, because the same dust that killed Opportunity coats the panels, and the great storms can choke the sunlight down to a tiny fraction of normal for months at a stretch, precisely when you can least afford an interruption in fuel production. So the serious plans reach for a nuclear reactor, landed on Mars and operated with no maintenance crew. A reactor brings its own demands, cooling systems that must not freeze or boil, shielding to protect the crew, and the grim reality that if anything goes wrong with it, there is no one within 140 million miles who can come and make it safe. The fuel plant's beating heart is itself another first, another machine we have never run on another world, another link that has to hold. There is one small, fragile piece of real progress I want to be honest about, because being honest about the limits means being honest about the hope too. On the Perseverance rover, which is on Mars right now, there was a little experiment, a toaster-sized device, that successfully made a tiny amount of oxygen out of the Martian atmosphere. A few grams, enough, over its whole operating life, for a small animal to breathe for a while. It was a genuine milestone, a real proof that you can pull breathable oxygen from Martian air. But I want you to hold that achievement next to the requirement. A toaster made a few grams of oxygen as a science experiment. The return trip needs the better part of 1,000 tons of propellant, oxygen and methane both, manufactured, chilled and stored. The gap between what we have proven and what we need is not a step, it is not even a staircase, it is a chasm, and right now we are standing on one side of it with a toaster, pointing at the other side and calling it a plan. This is the moment Feynman would have stood up. because this is exactly the kind of thing he caught at NASA. The slow, comfortable slide from "we hope this will work" to "this will work" to "we're planning as if this has already worked." The quiet conversion of a wish into an assumption. Nature cannot be fooled. The chemical plant either makes the fuel or it does not. And if it does not, no amount of public relations, no amount of live-streamed optimism will lift those astronauts off the ground. And there's a piece of the fuel plant plan that almost never gets said out loud, and when you finally do say it out loud, it rearranges how you think about the whole mission. The fuel cannot be made after the crew arrives. It has to be made before they ever leave Earth. Sit with why that has to be true. Manufacturing the better part of 1,000 tons of propellant out of the thin Martian air is not a quick job. It takes a very long time, well over a year of that hungry chemical plant, grinding away, drilling, heating, splitting, compressing, freezing, day after day, slowly filling the tanks. So the serious mission plans all do the same thing. They send the fuel plant ahead on an earlier launch window, uncrewed years in advance. It lands on Mars by itself. It deploys by itself. It starts making fuel by itself. And only once the tanks are confirmed full, only once there is verified, measured, sufficient propellant sitting on the surface ready to fly, do you commit a human crew to the journey. Because no sane person sends astronauts on a 7-month trip to Mars and only then finds out whether the machine that makes their ride home actually worked. But look at what that means. It means the single most important machine in the entire mission, the one the crew's lives depend on more than any other, has to run flawlessly untouched by itself on the surface of Mars for years before a single human is anywhere near it to fix it. No technician has ever set eyes on it running. No one has tightened a fitting or cleared a jam or swept the dust from its intakes. It is a chemistry plant the size of a small building, full of moving parts and catalysts and cryogenic plumbing and a nuclear reactor, and it has to do the hardest industrial process ever attempted off Earth, alone, for longer than most appliances last in your house, with a repairman a phone call away. And the moment you decide to trust it, the moment you light the engines that send the crew toward Mars, you have made a bet you cannot take back, on a machine you cannot reach, that has been sitting in the dust and the cold, doing the impossible without supervision since before the crew left home. This is the rocket equation playing its longest game. It doesn't just demand the fuel, it demands that the fuel exist verified before you're even allowed to commit. And it forces you to place the survival of your crew in the hands of an unattended machine on another planet, and then to launch toward that machine on faith that it kept working in the long silence after the last test signal. Nature cannot be fooled, and here nature also cannot be checked, not in time, not by hand. You commit and then you find out. Let me tell you about a robot that died because its death is a warning written in dust, and it speaks directly to everything the equation demands of the return. The Opportunity rover landed on Mars in 2004 and was meant to last 90 days. It lasted nearly 15 years. It became one of the most beloved machines humanity has ever built, trundling across the Martian surface, sending home photographs, outliving every expectation by a factor of 60. And then in 2018, a planet-wide dust storm rose up across Mars. The dust blotted out the sun. Opportunity ran on solar power, and as the sky darkened and the dust settled over its panels, its power drained away. It sent one last message, which has been poetically translated as, "My battery is low and it's getting dark," though that's a romantic paraphrase rather than its literal words. And then it went silent. NASA sent it more than 1,000 commands over the following months, pleading with it to wake up. It never answered. A 15-year survivor, a machine specifically engineered to endure Mars, killed by dust on its solar panels. Now hold that against the equation, because the very same dust, the very same storms, are what the return plan has to survive, not for 15 years, but through the whole critical window when your astronauts are on the surface, and your fuel plant has to keep running, and your vehicle has to remain flight-worthy. Martian dust is not like Earth dust. Earth dust gets rounded and softened by water and weather over time. Martian dust has been ground for eons by meteorite impacts and has never been touched by liquid water to smooth it, so each particle is sharp, jagged, microscopic broken glass. It's finer than the dust in your house, fine enough to hang in the thin air for months, and it carries a static electric charge that makes it cling to absolutely everything. It works its way into seals, into bearings, into joints, into any mechanism with moving parts where those sharp edges act like grinding paste, wearing precision machinery to death from the inside. And your Mars ascent vehicle, the rocket that has to lift your crew off the planet, is the most delicate, most failure-intolerant machine in the entire mission. Its engines have turbopumps that spin tens of thousands of times a minute, with clearances measured in fractions of a millimeter. Its valves have to seal perfectly against cryogenic propellant. Its fuel lines have to remain unblocked. And this machine has to sit on the surface of Mars for well over a year, exposed, while the fuel plant fills it, before it is ever asked to perform the single most violent and unforgiving task in the mission, the climb to orbit, the one that costs that 4.25 kilometers per second, the one where there is no abort, no second attempt, no rescue. If a single critical component on that ascent vehicle fails during its long wait, a seal cracked by the cold, a valve fouled by dust, a fuel line embrittled by radiation and temperature cycling, then the climb off Mars does not happen. And if the climb off Mars does not happen, the equation has delivered its verdict. The crew is on the surface. The fuel may be made. The path home exists on paper, and none of it matters, because the one machine that has to convert that fuel into 4.25 kilometers per second of upward velocity has failed, and there is no other one. No spare, no replacement waiting in orbit, no supply ship that can arrive in less than the better part of a year, assuming a launch window is even open, which for most of any given 2-year span, it is not. Opportunity was a machine built by the best engineers on Earth specifically to survive Mars, and Mars killed it with dust when its luck finally ran out. The return vehicle has to not get unlucky for over a year on its first and only try, with lives depending on it. The equation tells you how much velocity you must produce. It does not and cannot promise you that the machine producing it will still be working when the moment comes. There's a quieter enemy than the dust, one that works on the return vehicle every single night it sits on Mars, and it ties directly back to the fuel the equation demands. It's the cold. Mars is brutally cold. At night in many places, temperatures plunge well below -100 degrees Celsius, and across a single Martian day the temperature can swing by more than 100 degrees from afternoon to pre-dawn. Now think about what your return vehicle is full of. It's full of the propellant you so painfully manufactured, methane and oxygen, and those are only useful as liquids, which means they have to be kept colder than that even, hundreds of degrees below zero, or they boil into gas and bleed away. So you have this strange double bind. Some of your systems must be kept savagely cold to preserve the fuel. Others, the electronics, the valves, the moving parts, must be kept warm enough not to freeze solid, not to grow brittle, not to seize. And all of this has to be managed continuously through those 100-degree daily swings for the entire 16-month wait, using power that itself has to keep flowing through dust storms and frozen nights on a machine no one can service. Materials hate this. Every time something heats up, it expands, and every time it cools, it contracts, and a return vehicle on Mars goes through that expansion and contraction hundreds of times before it ever flies, once every single day. Seals that are perfectly tight at a comfortable temperature can shrink and leak in the cold. Rubber and plastics that flex easily when warm, recall Feynman's rubber ring, turn stiff and crack when chilled. Lubricants thicken or freeze. Metals grow brittle. Each cycle adds a little fatigue, a little micro damage, an invisible accumulation of stress, and the vehicle has to survive all of it and still perform flawlessly at the end. This is the same family of failure that doomed Challenger, cold making a material behave in a way the optimistic plan didn't account for, except now it's not one launch morning in Florida, it's hundreds of freezing Martian nights in a row with the nearest repair shop on another planet. And here is the thing that makes the cold so much more dangerous on the return than on the journey out. When you flew to Mars, your spacecraft was a fresh, factory-built machine, recently tested, recently certified, only months old. The ascent vehicle that has to bring you home is not fresh. By the time you need it, it has been sitting on the surface of Mars alone for well over a year, soaked in cold, scoured by dust, baked by radiation, cycling through temperature swings every day, with no one able to inspect it properly or replace what's quietly failing inside it. You are betting your life on a machine that has spent the longest, harshest year of its existence sitting unused in the worst storage conditions imaginable, and then you are asking it to perform the single most violent and unforgiving task in the entire mission perfectly on the first try. The equation says you need 4¼ kilometers per second. The cold spends the whole preceding year trying to make sure the machine that's supposed to deliver it won't. Part 6¾ There is no abort. I keep returning to a phrase, no second chance, and I want to make absolutely clear what it means, because it is the thing that separates the Mars return from every other dangerous thing humans have ever done. When a rocket launches from Earth and something goes wrong, there are increasingly ways to survive it. Escape systems that pull the crew capsule away from a failing rocket, abort modes that let a mission be called off and the crew brought back down. We've built entire layers of safety around the idea that if the launch goes bad, you might still walk away. On the journey out to Mars, too, there are at least some scenarios, in some mission plans, where a problem detected early enough lets you swing around and come home without ever landing, a free return trajectory, the cosmic equivalent of turning the car around. The ascent from Mars has none of this. Think about it. You are on the surface of a planet 140 million miles away. There is one ascent vehicle. There is no second rocket standing by to rescue you if the first fails on the pad. There is no escape system that can carry you to safety because there is nowhere safe to be carried to. There is no abort to orbit if the engine underperforms, because there's nothing in orbit to catch you and no fuel to try again. The climb off Mars is the purest all-or-nothing moment in the history of human exploration. Either the machine produces the velocity the equation demands cleanly on the first attempt in the narrow launch window the planets permit, or it does not, and if it does not, there is no version of the story where help arrives. The crew is simply stranded on the surface with no way up and no way home, waiting out whatever supplies remain. This is why honesty about the equation matters so much more for the return than for anything else. On Earth, we can afford a little optimism because we've built so many safety nets beneath it. On Mars, there are no nets. The optimism and the outcome are the same thing. If the plan is built on a hope and the hope fails, the failure is final and total and unreachable. There is no duct tape and a sock that mission control can talk you through, because by the time they even hear that something's wrong, the launch window may have closed. Nature cannot be fooled, and on Mars, nature also cannot be appealed to for a second try. I want to do something I haven't done yet in this video. I've given you the equation, the numbers, the history, the chain of things that have to hold, but I want you to actually stand inside the moment all of it is pointing at, because once you've felt it, the abstractions stop being abstractions. So picture it. Picture the morning the launch window opens. You've been on Mars for 16 months. You arrived a different person than the one strapping in now. Your heart has shrunk a little. Your bones have given up some of their density to the low gravity, quietly, the way sand leaves an hourglass. You've watched the fuel plant's readout climb, tank by tank, for over a year, trusting numbers you had no way to verify with your own hands. You've swept dust off panels 1,000 times. You've listened to the wind, if you can call that thin whisper wind, scour the side of the one machine that is supposed to take you home. And now the planets have lined up the way they do for only a handful of days every 26 months. And the window is open, and there is no waiting for a better morning, because there is no better morning for another 2 years, and you do not have 2 more years of supplies, or bone, or sanity. You climb into the ascent vehicle. It is not the gleaming thing that left Earth. It has spent the harshest year of its life sitting exposed in the cold and the grit, and you know that, and you climb in anyway, because the alternative is to stay here and die slowly instead of quickly. The hatch seals. And now comes the part that no courage can touch, the part that belongs entirely to Tsiolkovsky's arithmetic. The engines have to light, not eventually, now. On the first command, there is no second igniter, no backup vehicle on the next pad, no scrubbing today and trying tomorrow with fresh hardware, because there is no fresh hardware on Mars. If a turbopump that has sat frozen for a year doesn't spin up cleanly, if a valve fouled by that microscopic glass dust doesn't seal, if a fuel line embrittled by 16 months of temperature cycling cracks under the sudden surge of cryogenic propellant, the climb ends in the first 2 seconds on the ground, and the equation has rendered its verdict before you've risen an inch. But say the engine's light. Now you need 4.25 kilometers per second, and you need most of it in the first few minutes, and you need it from a vehicle that is, by mass, mostly the fuel manufactured from the air and the ice of a planet that was trying to kill you the whole time you made it. Every second of that burn, the equation is being paid in real time. The tanks empty at a furious rate. The vehicle lightens as it climbs, which is the only mercy the equation offers, the only reason the thing can accelerate at all. And it has to keep burning cleanly at full performance through the entire climb because you have no margin to spare. On Earth, a rocket that underperforms slightly can sometimes still limp to a usable orbit or abort to a safe return because there is an entire planet of infrastructure waiting below and beside it. Here, an engine that delivers 95% of its promised thrust doesn't get you 95% of the way home. It gets you to a velocity that isn't enough to make orbit on a vehicle with no fuel left to fix it, and there is nothing in the sky above Mars to catch you, and nothing on the ground to land back on with any gentleness. You either make the number or you don't, and the number was net in 1903. And here is the cruelest detail of those 9 minutes. Earth cannot help you through them. Even if every engineer who ever lived were watching, the news of your launch is still crawling across space, taking its minutes to reach them, and any instruction they could send would take its minutes to crawl back, and the entire ascent, the entire life or death burn, is over in less time than a single round-trip message. By the time mission control even sees the engine's light, you are already in orbit, or you are already dead. There is no talking you through it. There is no genius on the ground who can save this one, the way they saved Apollo 13, because the thing that saved Apollo 13 was a conversation, and across this gulf, in these minutes, conversation does not exist. You are the most watched human being in history, and the most alone, both at once, and the only thing in the universe that gets a vote is the equation, and it does not care that you are brave, and it does not care that a planet is praying, and it does not bend. That is the moment everything in this video has been circling, not the launch from Earth, with its towers and its crowds and its abort modes. This one, 9 minutes alone on a degraded machine, fueled by a chemistry plant you had to trust, off a planet that spent a year wearing your body and your rocket down, with no second chance and no help that can arrive in time, against a number written by a deaf schoolteacher before anyone had ever flown. Make it, and you go home. Miss it by even a little, and the films will end where the going ended, on the triumph, and quietly never mention the coming back. Hold that image, because now we have to talk about the problem that comes even before this one, the problem of how you get the machine that has to do all this down onto Mars in the first place. Part 7. The landing problem nobody has solved. There's a piece of this that sits underneath everything else, a problem so fundamental that it threatens the plan before the fuel question even comes up. And it's this: we don't actually know how to land something on Mars that's heavy enough to bring people home. I told you earlier that Mars's thin atmosphere gives you a gift on arrival, that it slows you down for free. That's true for small things. It is catastrophically not true for big things, and the reason is once again a kind of cruel physics. Mars's atmosphere is thick enough to set you on fire as you scream into it at thousands of miles an hour, generating brutal heat that you need a heavy heat shield to survive, but it is too thin to actually slow you down the rest of the way Earth's dense air does. So you arrive in this miserable middle ground. The atmosphere is dense enough to cook you but too thin to stop you. You get the worst of both worlds. Compare the two planets to feel how strange Mars's atmosphere really is. On Earth, the air is so thick that a returning capsule does almost all its braking just by ramming into it. By the time a parachute opens, the worst is over, and the descent ends gently enough that the whole thing can splash into the ocean or thump down on land under fabric alone. The air does the work. On the Moon, there's no air at all, which sounds worse but is actually simpler because you know exactly what you're dealing with. Nothing. You bring rockets, You fire them, you control your descent entirely yourself, no surprises. Mars is the cruel middle child. It has just enough atmosphere to heat you to incandescence and rip at your spacecraft and force you to carry a heavy heat shield, but nowhere near enough to finish the job and bring you to a survivable speed. It gives you all the costs of an atmosphere and only a fraction of the benefit. Every technique that works beautifully on thick-aired Earth, the big simple parachutes, the gentle terminal velocity, falls short on Mars, and every technique that works on airless worlds, pure rocket braking, gets sabotaged by the heat and drag of that thin air during entry. Mars sits precisely in the gap between our two proven approaches, belonging to neither, and that gap is exactly where a heavy crewed lander has to thread itself. For the small robotic landers we've sent, around 1 ton, we've built an elaborate, almost insane sequence to thread that needle. Take the way the Perseverance rover landed. It hit the top of the atmosphere at around 12,000 miles an hour. A heat shield bled off most of that speed through friction, slowing it to maybe 1,000 miles an hour. Then a supersonic parachute deployed, the largest ever flown at another planet, dragging it down to a few hundred miles an hour. But here's the thing, even with that giant parachute in Mars's thin air, the rover was still falling far too fast to survive a landing, so the parachute wasn't enough. A rocket-powered platform then fired its engines to slow the descent further, and in the final, almost unbelievable step, that platform hovered and lowered the rover to the ground on cables, like a sky crane, before flying off to crash a safe distance away. That entire baroque, terrifying ballet, the heat shield and the record-breaking parachute and the hovering rocket crane, all of it was the cost of landing 1 ton safely on Mars. Now here's the problem. A vehicle capable of carrying humans and the fuel and machinery to bring them home doesn't weigh 1 ton. It weighs somewhere between 30 and 100 tons, depending on the design. And the landing system we just described does not scale. You cannot just build a bigger parachute. The physics won't allow a parachute large enough to meaningfully slow a 100-ton vehicle in air that thin, and even if you could sew one, it would shred itself at supersonic speed. The sky crane trick that worked for a 1-ton rover is laughably inadequate for something 50 or 100 times heavier. The heat shield would have to be enormous. The carefully balanced sequence falls apart when you scale it up. So the honest, rarely stated truth is this. The largest thing we have ever successfully landed on Mars is about 1 ton. To bring people home, we need to land something 50 to 100 times heavier, and we do not currently have a proven way to do it. There are ideas, inflatable heat shields that deploy like enormous mushrooms to catch more air, using the rocket engines themselves to brake against the supersonic airflow, a technique that's only recently been demonstrated even on Earth. But none of these have been tested at the scale and in the conditions a human Mars mission would demand. We are not refining a solution, we are still searching for one, and I want you to sit inside the brutal arithmetic of those few minutes of landing, because they compress the entire impossibility into a span shorter than a coffee break. Engineers who work on Mars landing have a phrase for it, the 7 minutes of terror. From the moment a spacecraft touches the top of the Martian atmosphere to the moment it's on the ground is around 7 minutes, and every single step has to happen automatically, in sequence, perfectly, because the radio delay means Earth can't help in real time. By the time mission control on Earth even receives the signal that the spacecraft has begun entering the atmosphere, the whole thing is already over. One way or the other, the craft already landed safely or already a crater, and the people watching simply don't know yet which reality they're living in. They're cheering or grieving for something that already finished happening minutes ago, light still in transit. For a 1-ton rover, we've gotten that sequence to work several times, and each time it has felt like a miracle to the people who built it. Now make the falling object 100 times heavier, carrying human beings, and ask that same 7-minute automated miracle to work on the first attempt with no rehearsal at full scale and no possibility of intervention. The terror doesn't scale linearly, it scales with the mass, and the mass is the whole problem. Here's why the scaling betrays you, stated as plainly as I can. The drag that slows you down depends on the area you present to the air, roughly how wide your heat shield is. But the weight you're trying to slow depends on volume and density, which grows much faster than area as you make things bigger. So as you scale a Mars lander up, its weight outpaces its braking surface, and the thin Martian air, which was barely adequate for a small light craft, becomes hopelessly inadequate for a big heavy one. You fall faster, you have less atmosphere per ton to slow you, and you hit the ground still moving at lethal speed unless rockets make up an ever larger share of the braking, which costs fuel, which adds weight, which makes the problem worse. It is the exponential's cousin, a different curve, but the same flavor of cruelty, where making the thing bigger doesn't make the problem proportionally harder, it makes it disproportionately harder, until somewhere on that curve sits the human-scale lander we don't know how to build, and feel how this loops back into the equation. If you have to use rockets to slow your landing because the atmosphere and parachutes can't, then landing itself now costs delta V, which means it costs fuel, which means more mass, which means a bigger vehicle, which means you're harder to land, which means you need more fuel to land. The exponential, again, reaching its fingers into yet another stage of the mission. Every problem on Mars has this quality. You pull on one thread and the whole garment tightens around your throat. So before the fuel is even made, before the ascent is even attempted, there's a prior question with no current answer. How do you get the machine that brings people home down onto the surface in one piece in the first place? We can deliver a rover, we cannot yet deliver a way back. Let's say you grant every miracle so far. The heavy vehicle landed, the reactor running, the drills striking water, the chemical plant humming, the ascent vehicle's tanks slowly filling with methane and oxygen brewed from Martian air and Martian ice. The crew has arrived, alive, and stands on the surface. Surely now they can leave whenever they're ready. No, because there is one more tyrant in this story, and it is not the rocket equation, it is the solar system itself. And the cold geometry of how planets move. You cannot leave Mars whenever you want. You can only leave when Mars and Earth are positioned correctly in their orbits, so that the cheap coasting path between them, the same kind of free ride that got you there, actually exists. Both planets circle the Sun at different speeds, in different sized orbits, and the alignment that makes a return trip possible without absurd amounts of fuel only happens about once every 26 months. 26 months. More than 2 years between windows, so when your astronauts arrive, they cannot turn around. The window that brought them there has closed behind them, and the window home will not open for a long time. The optimal mission profiles have astronauts spending around 500 days on the surface of Mars, roughly 16 months, simply waiting for the planets to line up again, because the orbital mechanics give them no choice. And during all of those 16 months, the fuel plant has to keep working. The ascent vehicle has to stay flight-worthy. The crew has to stay alive and healthy and sane. Every machine has to keep surviving the dust and the cold and the radiation. And when the window finally opens, everything, all of it, has to work on the first try in a narrow span of days, because if you miss it, the next chance is more than 2 years away, and no mission carries more than 2 years of margin in supplies and fuel and human endurance. This is the timing tyranny layered on top of the fuel tyranny layered on top of the landing tyranny. The solar system itself sets a deadline that cannot be moved, cannot be negotiated, cannot be funded away. Mars and Earth will be where they will be, and when the moment comes, the verdict on whether anyone goes home is delivered not over years, but in the span of a launch window, by a machine that has been sitting in the harshest environment humans have ever tried to operate in, fueled by a process we've never run at scale, waiting to attempt the hardest maneuver in rocketry with no backup. The equation tells you the velocity you must achieve. The calendar tells you the only moment you're allowed to try. Part 8.5. What the weight does to a body. I want to dwell on those 16 months on the surface, because here is something subtle and important. That waiting period is not a choice. It's not that the crew lingers to do extra science, or because someone scheduled a long stay. The orbital mechanics, the same cold geometry we just described, force roughly 500 days on the surface whether anyone likes it or not. The planets won't line up sooner, and that means the rocket equation and the calendar, between them, sentence the human body to something it was never built to endure, as a precondition for the launch home. The physics of the return doesn't just demand fuel, it demands that the people who'll fly that ascent vehicle first survive a year and a half of slow degradation and then perform, at the end of it, the most demanding piloting task of the entire mission. Think about who has to fly that ascent. Climbing off Mars, threading into orbit, possibly docking with a vehicle waiting up there for the trip home, this is not a passive ride. It needs sharp minds, steady hands, good vision, sound judgment, fast reflexes. And the 500-day wait that the calendar imposes is actively dismantling every one of those things in the crew, day by day, in ways we understand well enough to be frightened by. Start with the bones. In the reduced gravity of Mars, around a third of Earth's, the skeleton is no longer doing the work it evolved to do. Bone is living tissue. It constantly rebuilds itself in response to the load it carries, growing stronger where it's stressed and quietly dissolving where it isn't. Take away most of the load, and the body, with brutal efficiency, starts disassembling its own skeleton, because it reads the lack of stress as a signal that the bone isn't needed. Astronauts lose bone density at a rate that, over many months, can strip away a substantial fraction of their skeletal mass. By the end of a 500-day stay, the very pilot who has to withstand the crushing acceleration of launch may have a skeleton more fragile than when they arrived. The launch itself, the violence of the climb, becomes more dangerous because of the weight the launch window forced upon them. Then the muscles, including the most important muscle of all, the heart. On Earth, your cardiovascular system fights gravity every second to push blood up to your brain. Take most of that fight away, and the heart, like the bones, downsizes itself to match the easier job. It weakens. Combine that with muscles throughout the body wasting from disuse despite hours of daily exercise, and you get a crew that after 16 months is physically a shadow of who they were on arrival, right at the moment they need to be at their best. Now layer on radiation, and here the physics of the journey and the chemistry of the equation conspire against the crew in a way that's genuinely hard to solve. Out in deep space and on the thin-aired surface of Mars, the crew is bombarded by high-energy particles, cosmic rays from across the galaxy, and bursts from the sun that slice through the body and damage the delicate machinery inside cells. The real protection against this is mass. Thick shielding, meters of water or rock or dense material between the crew and the sky. But mass is the one thing the rocket equation will not let you have in abundance, because every ton of shielding is a ton you have to launch, land, and eventually carry back up the staircase. So the equation that makes the fuel impossible also makes the shielding unaffordable, and the crew pays for it in accumulated radiation dose, in raised lifetime cancer risk, impossible damage to the heart and the brain and the very organs that filter the blood. The same tyranny that governs the fuel governs the protection. You cannot have enough of either for the same reason, and here is the cruelest loop of all, the one that ties the body directly back to the ascent. The kidneys, the organs that keep your blood clean, appear to be particularly vulnerable to the combination of altered gravity and radiation that a Mars mission delivers. Studies into long-duration spaceflight have raised real concern that the longer a body endures these conditions, the more kidney function may deteriorate, and calcium leached from those dissolving bones has to go somewhere. Much of it ends up in the bloodstream and then the kidneys, where it can crystallize into stones. A crew member doubled over with a kidney stone, or worse, with failing kidneys on the surface of Mars, has no real hope of treatment. There is no dialysis machine that survives that environment, no transplant, no specialist. The weight that the launch window forces could itself produce the medical emergency that there is no way to treat, in a place from which there is no rescue, so all of it set in motion by the same orbital geometry that controls when the rocket equation will finally let them leave. So understand what's really being asked. The return from Mars isn't a single hard moment, the launch. It's a year and a half of physical erosion that the calendar makes mandatory, ending in a demand for peak human performance from bodies the weight has deliberately weakened. The equation needs a healthy pilot to convert fuel into 4.25 kilometers per second of escape. The mission, by its very structure, guarantees the pilot won't be healthy. That contradiction sits at the dead center of the problem, and no one has solved it. You can't shield enough, because mass is forbidden. You can't leave sooner because the planets say no. You can only send people who are strong on arrival and hope there's enough of them left, 16 months later, to fly the only machine that can bring them home. I want to come back to staging, the one great loophole in the rocket equation, because there's something about it that I glossed over, and it turns out to be one of the deepest reasons the Mars return is so much harder than the trip out. Remember what staging is. To beat the exponential on the way off Earth, we build the rocket in sections and we throw each section away as its fuel burns dry, so we're never hauling empty tanks. It's the single most important trick in all of spaceflight. It is, in a real sense, the only reason we can reach orbit at all. And it works because of where we are when we do it. On Earth, where we have a vast industrial civilization that builds those multi-stage rockets in factories, fuels them at towers, and stacks them with cranes and armies of engineers. Now think about what that trick actually requires. It requires that you can afford to discard most of your machine. It requires that you have a fresh, fully built, fully fueled rocket sitting ready at the start. On Earth, that's just true. We make them in buildings. But on Mars, every one of those conditions evaporates. There is no factory to build a staged rocket. There is no crane to stack it. There is no tower to fuel it. There is no second one waiting if the first has a problem. Whatever ascent vehicle you use to climb off Mars, you brought it whole across the solar system, or you built it from almost nothing. You cannot manufacture a giant new staged rocket on the surface. You get what you landed, one machine. And that machine has to perform the staircase climb essentially in one piece, because the elaborate throw-it-away dance that saves us on Earth depends on infrastructure that simply does not exist on Mars. This is why the 4.25 kilometers per second to leave Mars is so much more dangerous than it sounds, even compared to Earth's 9.5. On Earth, we throw the worst of the exponential overboard, literally in stages, supported by the whole planet. On Mars, you have to swallow it more or less whole, with one vehicle, one tank of fuel you conjured from the air and the ice, one shot. The trick that lets us beat the equation at home is a trick you mostly can't bring with you. You arrive at the foot of the staircase a second time, having travelled 140 million miles, and you discover that the climbing equipment that got you up the first staircase has to be left behind, because it only works where the factories are. There's a haunting symmetry to it. Getting off Earth is the hardest thing we know how to do, and we only barely manage it by throwing our rocket away in pieces with the help of an entire civilization. Getting off Mars asks for a version of that same impossible climb, but performed alone on a hostile world with a single machine fueled by a process we've never run, after the people flying it have spent 16 months being slowly taken apart by the place. The equation is the same equation. The circumstances are the difference between a triumph we've achieved 1,000 times and a gamble we have never once attempted. The equation tells you the velocity you must achieve. The circumstances tell you that this time you have to achieve it with both hands tied. I touched on radiation when we talked about the body, but I want to come back to it on its own terms, because radiation is the place where the rocket equation reaches out and touches something that feels like it should have nothing to do with rockets at all, and that connection is one of the most quietly devastating ideas in this whole subject. Here is the problem in one breath. Out beyond the protective magnetic field and thick atmosphere of Earth, in deep space and on the surface of thin-aired Mars, the human body is exposed to two kinds of radiation that Earth shields us from completely. There are galactic cosmic rays, atomic nuclei flung across the galaxy at nearly the speed of light by exploding stars. And there are solar particle events, sudden violent storms of charged particles hurled out by our own sun. Both can tear through the body, breaking the molecules of life, damaging cells, scrambling the delicate code in our DNA. Over a long mission, this exposure adds up to a dose that meaningfully raises the lifetime risk of cancer and may damage the heart, the brain, and other organs in ways we are only beginning to map. Now, here is the part that connects it to everything else in this video. We know how to stop radiation. It's not a mystery. You put mass between yourself and the sky. Enough water, enough rock, enough dense material, and the particles are absorbed before they reach you. The deeper you bury yourself, the safer you are. On Earth, our atmosphere is doing exactly this. A blanket of air equivalent to about 10 meters of water over our heads, soaking up the cosmic rays so thoroughly we never even think about them. So the solution is known. The solution is mass. And mass is the one thing the rocket equation will not let you have. Do you feel the trap closing? Every kilogram of shielding you want to wrap around your crew is a kilogram you have to launch off Earth, push across space, land on Mars, and, for anything that travels with the crew, eventually lift back off Mars again, paying the exponential at every step. To shield a crew properly, the way Earth shields us, you'd need so much mass that the mission collapses under the rocket equation before it begins. So the planners are forced into a terrible compromise. They give the crew a little shielding, the structure of the ship, maybe a small heavily protected shelter to hide in during the worst solar storms. And then they accept that for the rest of the time, the crew simply absorbs the radiation and they manage the risk statistically as a raised probability of cancer years later rather than a wall they can actually build. The honest summary is that we do not protect Mars astronauts from radiation. We ration their exposure and hope it stays under a line we've drawn somewhat arbitrarily, because real protection costs mass, and mass is forbidden. On Mars itself, there is one genuine option, and it's worth mentioning because it shows how deep the compromise has to go. You can use the planet as your shield, bury your habitat under meters of Martian soil, or move it into a natural cave, a lava tube behind ancient volcanoes, and let the rock overhead do what your spacecraft couldn't afford to do. The radiation problem eases enormously when there's solid rock between you and the sky. But notice what you've traded. You've solved radiation by going underground, by living in a buried box or a cave, with no window, no horizon, no sky, for the better part of 2 years, on a world you crossed the solar system to explore. The shield you can afford on Mars is the one made of Mars, and it's bought with the price of never really seeing the place you came so far to reach. The equation doesn't just tax your fuel, it taxes your sunlight, your view, your sense of where you are. Everything in the end comes back to mass, and mass comes back to the equation, and the equation never, ever blinks. I want to take you back to a real moment in history because it shows you in flesh and blood why distance is the thing that turns every Mars problem from serious into possibly fatal. In 1970, Apollo 13 was on its way to the moon when an oxygen tank exploded. The spacecraft was crippled. The crew lost most of their power, their oxygen, their heat. By every reasonable measure, they should have died in space. And they didn't. They came home, against the odds, in one of the greatest rescues in human history. And the reason that rescue was even possible, the reason it could happen at all, comes down to one number. They were about 3 days from Earth. 3 days. That meant the smartest people alive could work the problem in something close to real time. Mission control could talk to the crew, get an answer back in seconds, test fixes on the ground, relay instructions, watch the results. They could improvise a way to scrub the carbon dioxide from the air using a sock, a manual cover, and duct tape because there was a conversation happening, back and forth, fast enough to matter. The crew was close enough to home that home could reach out and help them, breath by breath, hour by hour. 3 days from Earth, a catastrophe became a rescue. Let me make that carbon dioxide fix real, because it's one of the great stories of human ingenuity, and it depended entirely on distance. As the crippled spacecraft limped home, the air filling with the carbon dioxide the crew exhaled, the filters that should have scrubbed it clean turned out to be the wrong shape for the part of the ship the men had retreated into. Round filters, square holes in essence. On the ground, engineers dumped onto a table an exact copy of every single item the astronauts had with them, no more and no less, and raced to invent a way to connect the incompatible parts using only what was aboard. They came up with a contraption of plastic bags, cardboard, tape, and a sock, then read the instructions up to the crew step by step, watching, adjusting, confirming, and it worked. The carbon dioxide came down, the men lived. But notice what made it possible, a conversation. Question, answer, test, confirm, all in something close to real time, because the speed of light could cross the 3-day gap in just over a second. The rescue wasn't only courage and cleverness. It was courage and cleverness delivered fast enough to arrive before the crew suffocated. Now put a Mars crew in that same situation. They are not 3 days from Earth. At Mars, a radio signal takes anywhere from a few minutes to over 20 minutes to cross the distance one way. When the planets are on opposite sides of the Sun, a single question and its answer, there and back, can take the better part of 45 minutes. 45 minutes for one exchange. Imagine the Apollo 13 emergency unfolding with 45 minutes between every sentence. The crew reports the explosion. They wait, drifting, dying for the better part of an hour to hear "we copy, stand by." By the time any real instruction arrives, the situation has completely changed, or the crew is already gone. The rescue that saved Apollo 13 would have been physically impossible at Mars distance. The conversation that kept those men alive could not happen. The speed of light itself, the fastest thing in the universe, is too slow to save you that far out. And it's worse than just the conversation, because there's no rescue ship either. When something went wrong near the Moon, the entire might of Earth could in principle be marshalled. At Mars, even if you could build and launch a rescue mission the instant disaster struck, it would take months to arrive, and only if a launch window happened to be open, which, as we just learned, it usually is not. There is no Apollo 13 ending at Mars. There is only what the crew brought with them and what they can do with their own hands, in their own minutes, with Earth reduced to a voice that are of us too late to matter. I want to sit in that delay for a moment longer, because there's something about it that I think people underestimate, and it's psychological as much as practical. On the International Space Station, astronauts can talk to their families, to controllers, to friends in real time, a delay of a fraction of a second. The Earth fills their window, blue and alive and close. They are away, but they are not alone, because connection is instant. Now imagine the Mars crew. Every message they send home crawls across space for minutes before anyone hears it. Every reply takes minutes to crawl back. A simple exchange, "How are you?" "We're fine," takes the better part of half an hour. You cannot have a conversation like that. You can only trade messages, like letters, like notes left for someone in another time. Earth is no longer a presence, it is a memory you correspond with. And in an emergency, that delay transforms from a sad inconvenience into a death sentence, because the speed of light, the fastest thing the universe permits, is simply too slow to reach across that gulf in time to help. The crew is not just far away, they are, in the only sense that matters during a crisis, beyond reach. The whole brilliance and goodwill and expertise of their entire species is available to them and useless to them at the same time, separated by a delay that no amount of money or courage can shorten because it is set by physics itself. This is why the equation is so merciless about the returns specifically. On the way out, if something is wrong, in some scenarios you might be able to turn back, abort, limp home. Once you're committed to the surface of Mars, there is no aborting. There is no turning back. There is only the plan working or the plan not working. The distance that makes Mars a triumph to reach is the same distance that makes it a trap to be stranded on. Feynman's nature, which cannot be fooled, also cannot be hurried, and it cannot be reached for help across 140 million miles in time to do any good. I want to be very careful here, because it would be easy to walk away from this thinking the message is Mars is too scary or people aren't brave enough. That is not the message. The bravery was never in question. The people who would go to Mars are among the most courageous human beings who have ever lived, and the engineers who work these problems are brilliant beyond anything I can convey. This is not a failure of nerve or of will or of genius. That's exactly why it's so hard to talk about honestly, because the obstacle isn't a lack of any human virtue. The obstacle is arithmetic. Let me gather the whole chain into one place so you can feel the full weight of it sitting on a single mission. To get a crew off Mars, you need to produce 4¼ kilometers per second of delta V from the surface. The rocket equation says that requires an ascent vehicle that is 70 to 80% fuel by weight. That fuel cannot be carried from Earth, because the exponential makes the launch vehicle balloon to impossible size, paying the tax to carry fuel until the numbers run away, and because what you did manage to carry would slowly boil off across the long journey and the long wait. So the fuel must be manufactured on Mars, which requires drilling for water we've never extracted. running a chemical plant we've never operated on another world, powered by a reactor we've never deployed there, working autonomously and flawlessly for over a year. The machine that uses that fuel, the ascent vehicle, has to survive that same year on the surface intact through dust that has killed hardened robots and cold that embrittles metal and radiation that degrades everything, cycling through 100-degree temperature swings every single day. And it has to be landed on Mars in the first place at a weight 50 to 100 times heavier than anything we have ever successfully set down there, using technology that does not yet exist in proven form, through a 7-minute automated descent that Earth cannot even watch in real time. The crew that has to fly it has spent 16 months, mandated by the unmovable clockwork of the planets, having their bones, their muscles, their hearts, their kidneys, and possibly their minds slowly degraded by low gravity and radiation we cannot shield against, because the shielding is mass and mass is forbidden by the same equation. And when the moment finally comes, the ascent has to perform on its first and only attempt within a launch window dictated by orbital geometry, with no escape system, no abort, no rescue, and no help from Earth arriving in less than the better part of an hour or many months. Read that paragraph again, slowly, and notice that it is not a list of separate problems. It is one problem wearing many faces, and the face it wears most often is the rocket equation. The fuel is the equation. The mass that forbids the shielding is the equation. The size that makes the landing impossible is the equation. The boil-off, the staging you can't use, the impossible Earth-launched alternative, all the equation. Even the things that look like they belong to biology or chemistry or orbital mechanics are, underneath, the equation reaching its fingers into every corner of the mission. Because everything costs mass, and mass is the one thing the tyrant will not let you have. Every single link in that chain has to hold, not most of them, all of them. And if you assign even a generous probability of success to each link, the way you have to multiply probabilities together means the chance of the whole chain holding gets eaten alive, the same way the rocket equation eats your fuel. A chain of miracles is only as strong as the product of its weakest assumptions. And this chain is made almost entirely of things we have never done. Let me make that multiplication concrete, because it's the most important and least intuitive idea in Risk, and it's the exact thing that fooled NASA before Challenger. Suppose you're wildly optimistic. Suppose you say each individual piece of the return, the heavy landing, the fuel plant running for a year, the drill finding and extracting water, the reactor, the ascent vehicle surviving the weight, the launch succeeding on the first try, the crew being healthy enough to fly it. Suppose you say each of those has a 90% chance of working. 90% each. That sounds wonderful. That sounds like confidence. But probabilities don't add, they multiply. And when you multiply 7 90s together, 90% times 90% times 90%, 7 times over, you don't get 90%. You get something closer to 1 chance in 2, a coin flip. And that's with the absurdly generous assumption that every single never-before-done step works 9 times out of 10 on the first try, which nothing this new ever does. Drop each link to a more honest 80%, still optimistic for a first attempt, and the whole chain's odds collapse toward 1 in 5. The human mind looks at 90% on each line and feels safe. The math looks at the same numbers and sees a crew that probably doesn't come home. That gap between how safe the line items feel and how deadly their product is not a small psychological quirk. It is the precise mechanism by which good, smart, careful people talk themselves into catastrophe. This is the precise mistake Feynman caught at NASA, and it's worth saying plainly because it is the lesson that outlives him. The managers of the shuttle program had taken a series of individual risks, each one of which they'd convinced themselves was small, and quietly assumed that the whole stack of them was therefore safe. They had multiplied optimism by optimism and gotten a number that flattered them. Feynman went and asked the engineers, the people actually touching the hardware, and found that their estimate of the risk was hundreds of times higher than management's. The gap between those two numbers was where the Challenger died. Not in the rubber seal itself, but in the space between what people hoped was true and what the hardware actually was. The specific numbers from that investigation have haunted me ever since I learned them, because they're so human and so damning. When Feynman asked, the management of the program was working with a figure that put the chance of a catastrophic failure at something like 1 in 100,000 launches. 1 in 100,000. That would mean you could launch the shuttle every single day for hundreds of years and expect to lose it only once. The engineers who actually built and understood the machine, when asked the same question, gave numbers closer to 1 in 100 or 1 in 200. Sit with the size of that disagreement. The people responsible for the program believed it was 1,000 times safer than the people who actually knew how it worked. And the terrible thing is that neither group was lying. Management genuinely believed their number because they had slid comfortably over years of successful launches from "we got away with it" to "it must be safe." Every flight that didn't end in disaster felt like proof, when really it was just luck not yet run out. Feynman's whole point was that you cannot let the absence of disaster lull you into believing disaster is impossible. The dice can come up in your favor many times in a row and still, eventually, betray you, and if you've spent that lucky streak convincing yourself the dice are loaded in your favor, the betrayal will find you completely unprepared. That is the Mars return in miniature. Every robotic mission that has reached Mars, every rover that has landed, builds a comfortable feeling that we know how to deal with this planet. But we have never once done the return. Not the heavy landing, not the fuel manufacture, not the ascent, not any of it. The successful track record is entirely in the easy half, the going, and there is a powerful temptation to let that track record bleed over into confidence about the hard half, the coming home, as if the two were the same kind of problem. They are not. Letting the success of the journey out reassure you about the journey back is exactly the slide from "we got away with it" to "it must be safe" that killed 7 people in 1986. Nature kept the receipt. The Mars return is that same gap, scaled up to an entire planet. There is the version told in presentations, where each piece works and the chain holds, and the crew comes home to applause. And there is the version the hardware will actually deliver, governed by an equation written in 1903 that has never once bent for anyone. The whole danger lives in the distance between those two stories. And nature, as the man said, cannot be fooled. So is this video saying it's impossible forever, that humans will never stand on Mars and come home? No. I want to be as honest about the hope as I've tried to be about the wall, because honesty cuts both ways, and pretending nothing can ever change would be its own kind of fooling yourself. The word "impossible" in the title is doing a specific job. It is not saying the laws of physics forbid a Mars return the way they forbid going faster than light. They don't. A round trip is not against the rules of the universe. What it's saying is that with the technology we actually have today, proven, tested, real, not promised, the honest answer to "can we bring them back" is no. Not the way it's currently being sold. The equation, plus the things we have genuinely never done, add up to a return trip we cannot presently guarantee, and you do not send human beings on a journey whose return leg depends entirely on a chain of firsts. But equations don't change, and yet the inputs to them can. That's the door that stays open. The rocket equation has 2 real levers. One is how much delta V you need, and the other is how fast your engine throws mass out the back, which sets how much fuel a given delta V actually costs. We are stuck near the limit of what chemical fuel can do. The methane and oxygen, the hydrogen and oxygen. Those exhaust velocities are about as good as chemistry gets, and chemistry is what makes the Mars ascent so punishing. But there are other ways to throw mass. Nuclear thermal propulsion, where you heat your propellant with a reactor instead of a chemical fire, can roughly double the effective exhaust velocity, and because of the exponential, doubling that number doesn't just help a little, it slashes the fuel requirement dramatically. Beyond that, electric and plasma propulsion can do far better still, though at gentler thrust. None of these are science fiction. They are programs, some of them funded right now, some tested decades ago and shelved. The equation that condemns the chemical return might be survivable for a nuclear one. Nature cannot be fooled, but nature also offered us more than one kind of engine, and we have barely touched most of them. I want to dwell on that second lever for a moment, the exhaust velocity, because it's genuinely the most hopeful idea in this entire video and people rarely understand why. Go back to the staircase. The reason each step is so punishing is the exponential, and the exponential is driven by the ratio between the delta V you need and the speed your engine can throw its exhaust. Make the engine throw exhaust faster, and you shrink that ratio, and because it's an exponential, shrinking the ratio even modestly produces an enormous reduction in the fuel you need. This is the one place where the tyranny works in reverse, where a small improvement in the engine yields a giant improvement in the mission. A chemical engine throws its exhaust at a few kilometers per second. A nuclear thermal engine, by heating a light propellant like hydrogen to tremendous temperatures and blasting it out, can roughly double that. And that doubling can cut the propellant needed for a given maneuver not in half, but by far more because the exponential amplifies it. Suddenly the Mars ascent, or the journey home, fits inside a mass budget that chemistry could never afford. The crew might spend less time exposed in deep space because faster transits become possible. The fuel plant might need to make less. The whole impossible chain might relax into something merely very hard. This is not a fantasy. Nuclear thermal rockets were built and test-fired on the ground in the 1960s. Real hardware, real thrust, and then the programs were cancelled for reasons that had nothing to do with whether they worked. The physics is sound. We simply stopped. And the other piece of honesty is this. There is a sane order of operations that almost no flashy presentation wants to talk about because it's slow and unglamorous. Prove the fuel plant works at scale on Mars robotically before a single human goes, which the architectures already grudgingly admit. Solve the heavy landing problem with uncrewed test articles and watch some of them fail and learn before betting lives on it. Practice the whole brutal sequence somewhere closer first. The moon is 3 days away, not 7 months. An Apollo 13 distance, a place where a mistake is a lesson instead of a funeral. Learning to live off-world, to mine ice, to make fuel, to maintain machines through the long dark, on a world we can actually rescue people from, before we attempt the same on a world we cannot. That's not giving up on Mars. That's the only version of going to Mars that treats the people who go as something more than a bet against an equation. Let me defend the moon idea a little harder, because it's the most important practical point in this whole video, and it gets dismissed too easily as a detour. Everything that makes the Mars return terrifying, the fuel you have to manufacture, the machines that have to run for months untouched, the ice you have to mine, the cold and the dust and the radiation, every single one of those exists on the moon too, in its own form. But the moon has one overwhelming advantage that changes the entire moral calculus. It's close. 3 days close. Real-time conversation close. Send a rescue close. If your fuel plant fails on the moon, you learn why, you fix the design, you try again, and nobody necessarily dies finding out. If your ice drill jams on the moon, an engineer on Earth can talk the crew through it with a delay of a couple of seconds, not 45 minutes. The moon is the place where you get to make the mistakes that Mars won't forgive. It is the rehearsal hall, where a dropped line is embarrassing instead of fatal, before opening night on a stage 140 million miles away with no audience and no understudy. Every dangerous first in the Mars return, the autonomous chemical plant, the heavy precision landing, the long-duration life support, the in-situ fuel could be turned from a first into a tested, proven, boring routine on the moon within rescue range before we ever ask a human being to bet their life on it where rescue is impossible. To skip that, to go straight for Mars because the moon feels like old news, is to insist on taking the exam without ever attending the class on a subject where failing means you don't come home. Mars has been there for 4.5 billion years. It is not going anywhere. The rust, the dust, the thin pink sky, the buried ice, all of it will still be there in 50 years, in 100. The planet can afford to wait while we build engines worthy of the equation and prove the chain of miracles one careful link at a time. The question was never whether Mars will wait for us. The question is whether we can be honest enough, in the meantime, to admit what the math is telling us, instead of doing what NASA did before Challenger and quietly converting our hopes into assumptions because the assumptions are easier to sell. So let's come back to where we started, to the deaf schoolteacher with his pencil and to the dying physicist with his glass of ice water. Tsiolkovsky wrote an equation in 1903 that nobody could beat, and at its heart was a single cruel truth. The fuel you need to change your speed doesn't add up gently. It compounds, it multiplies, it climbs an exponential wall, and that wall is the reason space travel is so brutally hard, and the return from Mars hardest of all. We escape Earth only by the trick of staging, throwing our rocket away in pieces as we climb. But on Mars, there is no factory to build a second staged rocket, no tower to fuel it, no ground crew, no spare. There is only one machine, one tank of fuel you have to conjure out of the planet itself, one launch window, one attempt. The equation that we barely beat on the way up from Earth is waiting for us on Mars with none of the advantages we had at home. And Feynman, decades later, investigating why 7 people died in a fireball over Florida, distilled the whole thing into 8 words that should be carved over the door of every space agency on Earth. Reality must take precedence over public relations. Nature cannot be fooled, that is the equation no one talks about. Not really a single formula, but the union of the two, Tsiolkovsky's math, which tells you exactly what the universe will charge you to come home from Mars, and Feynman's warning, which tells you what happens to the people who pretend the bill is smaller than it is. The first one is written in symbols. The second one is written in the names of the dead. And both of them say the same thing about a human standing on Mars right now, today, with the technology we actually possess, looking up at a pale blue dot in a rust-coloured sky and asking the only question that matters, can I get home? And think about how strange and lonely that question would be to ask, standing there. Everything around you is the triumph. You cross the void. You touched another world. You are further from home than any human being has ever been. Standing somewhere no living thing has ever stood, and behind you stretches the greatest journey in the history of your species. The going was glorious. The going is the part they'll put in the films. But you are not asking about the going. You are asking about the coming back, and the coming back is the part the films skip, the part the slides hurry past, the part that lives in a paragraph nobody finishes out loud. You are asking it of a machine that has sat in the cold and the dust for a year. You are asking it of a fuel plant you have to trust made enough. You are asking it of a launch window that opens for only a handful of days. You are asking it of an equation that was written by a deaf schoolteacher before anyone had flown at all, and that has never once, in the entire history of spaceflight, given anyone a discount. The honest answer, the one the equation gives, and the one almost no one wants to say out loud, is that we don't know how to promise you that yet. Not because we lack courage, not because we lack genius, but because between you and that pale blue dot stands a wall of exponential math that was solved in 1903 and has never once been argued out of its verdict. You can fool an audience, you can fool an investor, you can even, for a while, fool yourself. You cannot fool the equation, and it would be the cruelest thing we have ever done. To send someone all that way on the strength of a number we already know is a lie we told ourselves. There's a version of this story where we get it right, where we don't repeat the slide from "we hope" to "it's fine" that killed 7 people over Florida in 1986, where we build the better engines that bend the exponential, where we make our mistakes on the moon 3 days from rescue instead of on Mars, where rescue is a fantasy, where we send the fuel plants and the landers ahead, uncrewed, and watch some of them fail and learn and try again until the chain of miracles becomes a chain of routines, where the first humans who set foot on Mars do so knowing, not hoping, that the machine to bring them home is real and fueled and tested and waiting. That version is possible. The laws of physics permit it. It just requires the one thing that's hardest of all, harder than the engineering, harder than the money. It requires us to be honest about what the math is telling us, even when honesty is slower and less thrilling than the dream. Mars will wait. The question is whether we're honest enough to make them wait too, until the day the math finally, truthfully, says yes. Because the people who go deserve more than a flag and a photograph. They deserve a way back. And right now, the equation no one talks about is still saying, quietly, that we haven't built it. Not yet. So that's the thing they don't put in the films. Not the launch, not the landing, not the flag. The quiet arithmetic underneath all of it, written by a man who never flew, refined by a man who watched 7 people die because someone decided the math was inconvenient. And maybe that's the real lesson here, and it's bigger than Mars. Tsiolkovsky and Feynman were separated by a century and an ocean and almost everything else, but they were saying the same thing in 2 different languages. The schoolteacher said it in symbols. The physicist said it in 8 words. Nature cannot be fooled, not by ambition, not by money, not by a beautiful presentation and a confident voice promising it'll all work out. The universe keeps an honest ledger, and it does not care what we hoped, or what we sold, or how badly we wanted the number to be smaller than it is. We will go to Mars, I believe that. Maybe not the way it's being sold to us, maybe not on the timeline anyone's promising, but we'll go. The question was never whether we're brave enough, or clever enough, or determined enough. We are all of those things. The only question is whether we're honest enough to look at the equation and say what it actually says, instead of what we wish it said. Because the people who finally make that journey, the first ones to stand on the rust and look back at a pale blue dot and come home, they won't get there on the strength of a dream. They'll get there on the strength of the truth. And the truth, for now, is still waiting on a better engine, a braver kind of patience, and the courage to admit what the math already knows. Not yet, but not never.